the goal of today, 4 forces operate and how they operate in relation to a helicopter. Induced flow, transverse flow, ground effect, translating tendency, toning, Coriolis effect, gyroscopic precession, translational lift, effective translational lift, and auto rotation. A lot to get through. This is only, I have 103 slides for today, yes? Okay, I need you with it, okay? You'll have a quiz probably on Friday on just rotorcraft, okay? My class is packed, you got no choice. They're just going to keep coming, okay? Desire today is to understand basic helicopter aerodynamics. The student can understand and identify basic aerodynamic factors in relation to a helicopter. Okay, your book. Hopefully helicopters are more elaborate in your new books. Any questions so far? What we're going to be covering? Okay, you do have a new lab today. You'll have a lab tomorrow as well. All right, any questions for a roll? Okay. I don't think I put the chapter in there. It's in assembly and rigging, or it should be flight controls. All right, how many of you have flown in a helicopter? All right, we've got quite a few. Wow, good. All right, are you certified pilot for a helicopter? Or you just have hours training?
I have hours.
Okay. Anybody else have hours of training in a helicopter? All right, so how does a helicopter actually work? How does it work? Beats the air in submission, okay. So the way we think about it, if you want to understand a helicopter, don't think of it as having a big fan on top and a smaller fan on the back. Think of it as having rotating wings. Okay, rotating wings. Why? How does an airplane operate, Tempe? What's the 4 forces that affect a airplane?
You have lift, thrust, drag, and gravity.
Okay, so lift, weight, thrust, and drag. Good. So angle of incidence is the angle between the chord line and the rotor disc. Little different there. How's that different, Elijah? Well, this is considered the rotor disc itself, and yes, this disc area does move. Okay, but what is the difference between that and like what you would say on an aircraft chord line? Most of the time, yep. Except for what? Yeah, like your Navy aircraft, okay. Or stabilators change angle of incidence as well. But on this one, we're constantly changing, okay? Depending on the type of rotor head that it has, okay? Angle of attack is the angle between the chord line and the relative wind. Does that sound familiar? Everybody good there? All right, good deal. So rotor disc provides lift and thrust at the same time. As it goes around, it provides lift and thrust at the same time. We have induced flow, we have transverse flow. Induced flow is the downwash produced as a blade pitch angle is increased. Recirculating air, dirty air, okay? So a helicopter comes in, getting close to the ground. What's happening? Yeah, it's bouncing off second. But more than, as it's sitting there, it's taking in that dirty air, recirculating, okay? And that could be potentially dangerous. But transverse flow is induced flow is redirected through the aft part of the rotor disc as the helicopter transition to forward flight. So we take air and it's transitioned this way instead of recirculated. Okay? Horizontal air. Horizontal air. Okay. We have Iggy and Ogie. Iggy and Ogie. And then we're going to get to Higgy and Hoagie. I'm not lying. I'm serious. Iggy and Ogie, Higgy and Hoagie. Iggy, rotor disc is more efficient due to airflow, downwash, in ground effect, striking the ground, and it's not a cushion of air. So, the way you think about Iggy, as a helicopter comes down towards the ground, okay? As an aircraft comes down towards the ground, what's going to happen to the aircraft as it gets over the runway? What? It's going to get in ground effect, which means what? Huh? In a float. So the air coming over the wing does what? Pushes, and the air under the wing, which is causing lift, has nowhere to go. Okay? So it's pushing down on the ground, which gives us a, well, sometimes they refer to as a balloon effect, right? You can get a little extra balloon, depending on your speed, but it actually will help the aircraft with this lift. Well, with a helicopter, as it comes down, it's pushing down that air, and the air has nowhere to go. As it comes through the top of the rotor, heading down towards the ground, it's got nowhere to go, so what happens? It creates a pressure underneath the helicopter, not a pillow of air, not a cushion of air, okay? It's a pressure. It increases the air pressure underneath the main rotor disc or the helicopter itself. So, Higgy, hovering in ground effect, is equivalent to one rotor disc distance from the ground. So, if it's a bell, it's like stinking 50 feet, right? It's like 40 something, but it's huge. Okay, if it's the roadway, what is it, 20 feet? Your hovering ground effect is about 20 feet, one rotor disc. You'll need to know that. Higgy, Hoagie, Ogie, and Odie, Iggy and Ogie. So, out of ground effect is less efficient due to loss of increased air pressure. Okay, so for a helicopter just to sit in midair, okay, just to hang out. Woo, yeah, super cool. Hang out. What's the potential danger? There's no increased pressure underneath it. Okay? So, vertical ascent on a hot day can lead to rapid descent and settling with power. It's called a vortex range state. So, what's the bad mojo here is we get a helicopter, and unfortunately, we're in Denver, Colorado. Okay, so we get super heavy. We load this bad boy up. It's super heavy. Super heavy, okay? And we're in Denver, Colorado, which is what? High elevation. And it's heavy aircraft, and for once in Denver, it's 85 degrees, okay? So what's the potential danger? Rapid descent, because our air is thinner, okay? And so we're trying to get air through there, and now we're hot and heavy. Oh, man. We're not going to get as much air or density of air through the rotor, okay? So what's the potential hazard? Oh no, we're going to start recirculating because we're trying to hover, okay? Trying to hover. I'm going to put this guy beside you. They're going to bother you. I'm going to hit you. Okay. All right. So, 3 difficulties or dangers. That's hot, heavy, and high elevation. Yep.
Is the rotor both blades, or is it just one blade?
The rotor disc?
Yeah.
It's the full, it's both, it could be all five, whatever the circle is, yep. All right. So, here's vortex ring state. This is somewhat a sprayer way high up, okay? We're losing efficiency as the air is then what? What happens to the air? Recirculated back through the disc. See that? It comes off and then it's recirculated back through, recirculated back through, recirculated back through. Okay? And so now we have no forward airflow. We're just taking the same air and putting it right back in. This could lead to a potential uncontrolled descent and crash. Because our lift needs to go just like it does on a aircraft. We have to get lift. We got to do what? We have to get air going across the top of the blades. Same thing. We got to get air going across the top of the blades. And if we're just taking air off of it and then recirculating back through, there's no forward momentum of the air. So we're just recirculating that air. Air is already unstable, could lead to a rapid descent. So how do we get out of this? How does a helicopter pilot get out of the vortex ring state? You gotta go to forward flight. So the ship has to go lean down and enter forward flight to get downwash through the rotor blades itself. Okay. Pretty good as far as intro yet. We're still very basic with helicopters. We're going places. Yep. Everybody good?
Why does it want to do that? Is that because there's denser air rising from the bottom or something that it wants to go back around?
Yeah, well, you're building a vortices. Yeah, so it's hitting this heavier air down here and then just going right back up because you're separating the air. So as it hits the heavier or denser air down here, it tries to lift and you're just pulling it right back through as you're hovering there.
Is it kind of like the easiest?
Yeah, it's the same. Let's not say the same, but yeah, general idea of when you get vortices. Okay, but you're losing because you're separating the air every time that you're. I'm not gonna say you're feeding the air into submission, but the same thing. But every time the rotors come through, you're separating that air. So now, man, you're really unsettling the air, and then you just keep unsettling it over and over again. He's really descending here.
Can you explain back from one of the first slides you said about it's not a cushion, it's pressure? What's the difference?
That's in ground effect. So, in ground effect, all right, so this is our runway or whatever pad that the helicopter decides it wants to land on, right? So here comes the helicopter, comes down, he's coming down, and so one rotor disc, underneath it, between the rotor disc at the top, the little spinny thing on top, and the ground, where's the air going to go? If he's just sitting here hovering, hanging out, okay, Iggy and Ogie. Iggy is what? In ground effect, and this helicopter is Ogie. What's Ogie? Out of ground effect. So in ground effect, the air from the rotor itself is pushing against the ground. So you're increasing that pressure, which then what does what? The air can't run away, right? So if it's recirculated fine, it's just going to push against the ground there. Okay? If it's a hot day, yeah, it could be really dangerous. But a normal day, like maybe today, okay, you're pushing against that ground, you're going to get a ground effect. So it's pushing against the ground to give it not a cushion of air, an increased pressure. Put your friend back. Okay.
Yeah, let's say if that rotor disc is 20 feet, that's from 20 feet up all the way down, or is it just that around that 20 feet?
You're 20 feet up. Okay, there is a slightly danger when you get real close to the ground, but for the most part, it's if the bell could be 40 feet to down. Yep. All right. So, Zach, what is ground effect?
For helicopters?
Yep.
It's where you increase the pressure below the rotor.
Good. You're increasing rotor efficiency due to ground reducing the velocity of air, which increases the, because the air can't speed up because it's got nowhere to go, right? Hit the ground, hit the ground, hit the ground. Okay? Not a cushion of air. All right. What's distance determines ground effect? Typically 1 rotor diameter distance from the ground. Okay. Translating tendency. Tendency of a helicopter to move in direction of the tail rotor. Okay. How do we see this, Mr. Erdy, on our fixed wings? On our fixed wing, airplane, fixed wings, how do we see this?
How do we see gyroscopic precession?
No, just your translating tendency. What do you see? Let's not go gyroscopic precession yet. Torque. Where do we see the torque at? Most.
Takeoff.
Takeoff. Okay? So for a helicopter, this big giant spinny thing is going to want the helicopter to torque. Okay? And so you're watching this helicopter torque. You get a drift, but it's also going to torque. And it's going to torque the opposite direction of the blade rotation. Okay? All right. So in our aircraft on takeoff, your GO, does it go right or does it go left? It goes opposite. So do you have a different translation? Okay, it does. All right. Some of those geared engines with it do opposite. All right. So on a aircraft, our propeller's sitting out there turning, and we're going to push which rudder? Right rudder on most of our aircraft. Okay. Here, as the blade's rotating this way, our torque's going to try to drive this way. So we have a tail rotor to compensate. All right. So translating tendency. What's the definition of translating tendency? Tendency for a helicopter to move in the direction of tail rotor thrust, and is offset by the main transmission canted to the left, and flight control riggings to the left. So that mast won't always be dead center of the helicopter. Maybe slightly offset, maybe an inch, maybe 2 inches, to compensate for translating tendency that the helicopter will have. Okay? All right. Centrifugal force and upward lift component causes blades to curve up. Whoa, upward. Upward. Upward lift and component causes the blades to curve upward. So the blades actually will curve up as the airplane's sitting there doing the spinny thing. Rotorcraft's actually doing the spinny thing. So the blades are actually going to curve slightly up. Okay? Referred to as coning of the wings. Anybody know? Can you name that airplane? Anybody know? Going once? No. Going twice. Gavin?
I don't know the name, but isn't that the one that went around the world the last
Yeah.
time?
Yes. On it. The Voyager. Like, wasn't it Dick Rutan? Bueller. Dick Rutan. But notice the wings here. Coning. Straight up coning, okay? It's not such a big deal. It is slightly a big deal, but not a huge deal with fixed wing. With helicopters, it's a big deal, okay? It's a big deal. And I'll try to make this less math and more understanding here. Hopefully I can help you with that. All right? So, lots of helicopters, okay? And the idea is they're going to cone. Even if they have 5 blades, they're going to have a slight coning as it's spinning around. Okay? That's just crazy. Wow! Okay. All right? And it also depends on type. If we have a rigid, semi-rigid, and fully articulating head on the blade. So all that, just say, well, how much do they cone? All that's dependent upon how it's designed, okay? So, anyway, we'll try to get a little bit into that. This one, you can see the rotor cone here, where this one's kind of straight, and this one's coning up a bit. All right, everybody with me? Everybody awake so far? Okay, because we are moving places. What causes translating tendency, Parker, on your birthday? All right. Make it simple. You're talking to people like me. Make it simple, please. Nope. Just think about the thing on top. What's it doing? What's the thing on top of the ship doing? Spinning, right? And so what's going to happen with the tail? Do what? Yeah, so your torque's going to drive opposite of the blade rotation. So if the blade's coming this way, which in America most are counterclockwise anyway. So we're going counterclockwise or whatever, and then the tendency is for this tail to go towards the blade direction. Okay, so it's going to come this way is the torque tendency. Okay, all right. So tail rotor thrust, translating tendency. Okay, Coriolis effect. Okay, can we go back? Any questions on this? Yep. Well, so is it possible to do forward flight if the aircraft, the rotorcraft is constantly doing this?
No.
Yeah, so we're going to have we're going to use a tail rotor. Tail rotor is going to spin up, and the blade angle is constantly changing. The little rudder pedals for the pilot in here, constantly changing to keep the tail in the direction you want it to go. Okay, because over time we're going to just keep doing this.
Looks like you're crashing.
Okay, it's just doing a dance in the air, right? It's not really getting anywhere. Now, you don't buy helicopters to go fast. You buy helicopters to spend money. So, and to land anywhere, but really to spend money. That's the goal of a helicopter. Well put. I'm not ever seeing a cheap helicopter. Well, maybe. They just don't have the rotor up top anymore. Coriolis effect. You'll need to know this forever and ever, especially for the writtens. Angular momentum. Distance times mass times distance from the rotational axis squared times speed of rotation. Josh, did you get all that? Okay, good. So I'm going to mesmerize you by an Olympic skater. Okay. Sorry, it's not a hockey skater. It's going to be one of those figure skaters. Woo, okay. All right. So we have a 2-foot radius. And what do they do in the Olympics, right? They spin stupid fast. And then when they're getting stupid fast, what do they decide to do? Stand up, which makes them do what? Nailed it. You're with me this morning. Go faster, right? So they're out here spinning. So you have a 2-foot radius. Here's the mast. Sorry, we're talking about helicopters with skaters. So 2 foot. Well, let's say the leg maybe weighs 50 pounds. Probably not. It does have a skate on. So let's say 50 pounds. So 50 pounds, and then 2 foot radius times 2 at 30 RPMs. We have 6,000 foot-pounds, okay? 6,000 foot-pounds. What's the problem with this? She's going to do what? All these skaters decide they want to show off, and so they're going to do what? I'm not going to try it. So they're going to do what? They're going to stand straight up, which does what to our Coriolis effect? Our radius just got a whole lot smaller. And because they're tinier people than myself, they decide that they're going to get even tinier, right? So now we have a 6-inch radius from the center of the mass. So, you know, they get super tiny, but what's the problem with that? No, it's actually more stable, but you have less torque because my radius has just done what? Cha-ching! Gotten super small. So to get the same foot-pounds, what needs to happen over here? You got to spin a whole stinking lot faster. So right here, we're going 30 revolutions per minute, probably a lot more, but 30 revolutions per minute. So now, in order to do this, how fast do we need to go? What's our revolutions now to get 6,000 foot-pounds? How many revolutions per minute do we need now? No. Yes.
What's the radius?
Radius, 6 inches, so it's half a foot, because we're doing it in foot-pounds. Okay, anybody solve for it? Da, 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 da. 480. 480. So 480 RPM. So do you see a difference? Whoa, wait a second. So when the helicopter's going around, what happens to get the same torque? These little thingies begin to do what? And as they begin to cone, what's going to happen to our rotor? Faster. In order to keep the same amount of lift or torque, now as it begins to cone, what's the problem with it coning too much? Overspeed. Okay? So we have a greater tendency with helicopters to overspeed, okay, as it's trying to grab the air and lift. We have a greater tendency, because of Coriolis effect, that we could overspeed or over RPM our actual engine. Okay? That's no bueno. Okay? What's the potential danger if we overspeed? Things are coming off. Yeah, they're coming off in a hurry. Okay? And you thought a rock fell fast? Yeah. Harder.
What scenario would you be able to overcome?
Say it again, I'm sorry.
In what scenario would you actually be able to overcome?
So typically that's going to be in a dead lift area, okay? Because everyone wants to stink and go straight up in the air, right? In the helicopter. Oh! Okay? So to overcome that, you got to get some air across those rotor blades pretty quick. And go to a forward translation instead of a dead straight up, okay? Because man, when you're sitting there slow, trying to keep the torque centered, and your blades are really going to have to be working, okay? Because they don't have a fresh airflow coming through as a downwash across the blades.
So does this, the Coriolis effect, or the coning, whatever, does that happen when you're hovering, or when you're going straight up, or both?
Yes. Yes. It does. Yep. It actually happens all the time, but your greater potential for overspeeding is when a deadlift or yeah, hovering. Yeah. Yes, sir.
Is overspeeding common in helicopters?
Not if they're going to survive. Yeah, it is common. But did you ever get yelled at? Or
Yeah,
someone?
it depends.
Yeah, never overspeed or never exceed,
Yeah. So what's the data, so?
just like fixed wing. But this one, it can happen very quickly. It could happen, especially if you're full RPMs and you're in a dead lift. Like Paul is working in Howell, Michigan, and that's all they do. They're building a new plant down near Battle Creek, and he had to do 500 air conditioners from across the road. They had to deadlift, and so he's the hookup man and the one that has to fix it. So fix the helicopter. So he's like, we're just deadlifting all day long across the road. So that's what that helicopter's doing. Okay? Any questions? Let's hit this. I'll give you a break. Oh, wrong one. Okay? What's the axis of rotation? Axis of rotation up through the middle. We have a radius. What would cause the radius to change in a helicopter? Coning. Centrifugal force or lift causes coning because we have to get the blades, and as we lift it, the blades begin to lift up, giving us a cone effect. Okay? Oh, you named it. I didn't even get a chance to say it. Go ahead and say what it is.
Sky crane.
Sky crane, okay? Sky crane, and here's where we get into hoagies and higgies. Notice, what do you see with the blades? Serious coning going on. Okay? Lots of blades out there, serious coning going on. Because what is the ship doing? It's hovering, okay? So, what is higgy again, Josh? Yes. In-ground effect. Hoagie is over at Jimmy John's. It's not. So it's hovering out of ground effect. So higgy will have a downward pressure on the ground versus hoagie is up here in the air. We have a chance of recirculating vortices to get dirty air across our blades. Okay. So now the blades are really having to work. Okay. We don't want serious danger right here of overspeeding our blades. Just think of the figure skater going too fast. Yep.
So is out of ground effect, is that when it's going up and in ground effect when it comes down?
No. Out of ground effect is above one rotor disc. So if you look at the bell out there, it has a humongous rotor on top of it. It's like 40-something feet or something like that. And so you say, okay, 45 or 44 or 50 feet, basically, from the ground up is ground effect. Anything above that is out of ground effect. Okay? And you guys didn't see it, they didn't do it this year. What a bummer. It's typically the Blackhawks will come in here and they'll do whiteouts. They'll just practice doing landings right on the runway in wintertime. And you'll see them come in, because this is where it's super dangerous. They'll come in to our runway and they'll practice doing low approaches. And they'll get in ground effect. Well, during snow time, what happens? They pull it all back in, and then you can't see a thing. So then the pilot has to raise up, get out of the ground effect, and then get back in, but then they have to come in very quickly with the snow. Otherwise, they'll pick it back up, and then there's a whiteout again, and then they come back up, get out of it, and you watch them 3 or 4 times, it looks like a frog. Come down like they're going to land, oh no! And it whites out, and then back down, and then whites out, and back up to get out of that. So, I was hoping that was going to happen this year. We'd be able to see just how much snow they pick up when it's real light like that. Okay? Yes, sir?
So, in ground effect, you would have build more air pressure underneath, right?
Yes, sir.
So at that point, you would think there would be more pressure pushing the blades up for coning. Why is it the opposite?
Well, you have a natural lift. You have natural lift. Oh, I guess it's unnatural.
More because you need more RPM to keep up, to stay up than it cones?
Correct. Yeah. As it's trying to grab the air, because you have more air here pushing up in ground effect, okay, which is going to give you a natural rise. So then typically Okay, I don't need as high a RPM to maintain. When I'm out of ground effect, I'm increasing the RPMs to hold myself there. Oh no, I start falling, okay, because the air is now getting a dirty or what we call vortex ring state, because we're getting air back through. So then they're increasing again. Now we're at the danger point. Because now as the blades begin to come up, now honestly in Michigan I don't think you would have too huge an issue. It was if you were really heavy or if it was hot, where you would really see that. But yeah, you don't have as much pushing up back on the blade. Hey, why don't you guys take a break, come back I'll give you till 8. All right. Radius reduced, increase RPM, increases lift. This can affect, which increases lift, but affect blade track and rotor RPM. Okay, so quick review. Let's see who the first contestant is. Elijah, congratulations. Oh, sorry. Why does Coriolis effect matter in a helicopter?
Because you don't want your blades to overspeed and stuff.
Oh, okay, good. All right, I just gave you that. No, you already had it though. All right. Now, something a little bit scary. All right, are we good? All right, here we go. So, dissymmetry of lift. Without lift, we going down. Okay? Unequal lift as blades travel around the rotor disc. Okay? Caused by aircraft speed, blade position and rotation, and rotational velocity. Okay, so someone asked me, and hopefully I'll answer this. Does the pilot control Coriolis or coning? The Coriolis effect or coning? Does the pilot control it? No, it is reactionary. Oh no, the blades are about to fold over like a Navy, what plane was that? The old Navy plane that would fold up the wing. Corsair, oh no, like a Navy Corsair. No, we don't want that on a helicopter, okay? So what do they say is, oh no, so they got to slow the RPM but also maintain lift. So dissymmetry of lift, now this is really contingent upon how the blades are designed, okay? So you get a semi-rigid, which is a seesaw. We'll sit there and seesaw. So one blade's up, one blade's down. How does that happen? Okay, so that's where we get to gyroscopic precession, which we'll talk about. But you get this dissymmetry of lift where you have one blade that's really going up. What's going to happen? That's where they're really trying to get some lift across that one, okay? Versus the other one's cutting through, cutting down, okay? Now, I know this is tail rotor, but just imagine it's main rotor. If I brought a main rotor in here, it'd be a little bit tight, okay? So, aircraft's airspeed, blade position in the rotation, okay? And that has to do with gyroscopic precession because they can't just say they want the blade to go up here. They actually have to make a change at 90 degrees for gyroscopic precession for the change to actually affect it by the time it's at north and south or forward and aft. So, and then lastly, rotational velocity is affects dissymmetry of lift as well. Okay? So we have the blade is turning counterclockwise, which is typical in the U.S. Okay? There's other ones that are clockwise, Europeans, whatever. Okay? Whatever. So we have a blade that's going 360 knots, okay? And then we have a blade that's going what? So rotational velocity is 480 knots. But because the wind's pushing it this way versus the wind's pushing it this way, what happens? We have a wind velocity of 600 knots versus 360 knots. So you have an advancing blade versus retreating blade. So advancing, retreating. So you have a aircraft speed, because the aircraft's going in forward flight, negative 120. Air's coming across, it's pushing that blade. Okay? Versus the forward blade is having to is hitting the aircraft airspeeds, actually hitting the air, its wind velocity of 600 knots. Okay? See if I can show you a depiction here. Oh yeah, I do have it. Sweet. Okay, so the other day, I think it was Gavin, but maybe I'm wrong. Please forgive me if I'm wrong. Can't remember who it was. But we were talking about head-on collisions. Okay, so you're driving in your car and you hit somebody head-on, unfortunately. Okay, what is the force created here? 80 mile an hour of force against each other. Boom! Okay? You got an 80 mile an hour crash because one was going 50, one was going 30. Okay? But say you're going 55, Corbin, 65, whatever it is, and I'm going 55 or 60 on 44 on the way to school, because I normally see these big headlights in the back of my car. Okay? So here's the old guy, old short guy here, and here's the Hummer. Okay? And he comes up on me, and he hits me because he's late, right? So what's the impact that we have here? Only a 5 mile an hour crash. Now it wouldn't be that bad. It would be bad for my Acura, but not so bad for the Hummer. Okay? So for the blade coming through here, we have 80 mile an hour. So we're increasing. We have a rotational velocity as it's increasing. Here's 600 knot wind velocity versus the wind direction as the relative wind's coming back. It's pushing the blade backwards. Okay. So as the blade goes up, see if I can show you this. Hopefully, as the blade goes up, this direction as our blade goes up. What's a potential danger? If the blade angle is very, very high, what's a danger?
Critical angle attack, stall.
Yes, you could stall one blade. Okay? You could stall one blade if it reaches a certain critical or beyond the critical angle of attack. Okay? You could actually stall one blade, which then, you know, the ship itself would then lose lift on that side and fall over. Okay? So that's potential hazard that we have of coning, severe coning. Okay, blade comes up, it's going to spin a little faster, trying to maintain that lift or increase the lift. We could overspeed or get too high of RPM. Increased lift, decreased lift. Okay, so it's pretty easy to see on our bell because it's a seesaw. That whole drive mechanism is a semi-rigid, so you get a seesaw effect where this blade will be up, this blade will be down, and it's designed that way. Pretty cool. But as Tim Peake was asking, at what point, what's holding that blade on? What's holding this blade on? Couple bolts and the design of it. Okay? And so, man, those blades are stressed. Yes, sir?
So, because you got a lot more wind velocity on the right side, so you would think it would start to lift more on that side versus the other side. How do they compensate?
That's where we get to speeds. Lead and lag. And it's slightly different layout based on design where you have a rigid system which the blades are stressed way more, or we get to a fully articulating where one whole side of the mass will drop down to compensate for that. So I'll try to get to it today, and I think it'll make more as you start to see the different types of heads, how that actually happens. Okay. For now, just realize that you have an advancing blade versus retreating blade, and there's potential for dissymmetry of lift, which is going to happen. One side's going to lift more than the other, okay? And so they tell you as a helicopter pilot, now I'm not a helicopter pilot, but you're never never chilling. Okay, there's not this mode where you just, hey, let's just relax, right? You're always doing something with your feet. You're always doing something, not necessarily with the collective, but the cyclic, you're always doing something with the cyclic. And the rudder pedals, just trying to maintain where you're at. So it's not like a straight level hangout flight. Okay, what are 3 factors that could cause dissymmetry of lift? 3 that lead to it. Okay, airspeed is 1, good. Airspeed in relation to the wind speed. Airspeed, yep. Sydney, what's the second? Yeah, blade rotation speed. Okay, Sam, do you have another one?
Position of the blade in rotation.
Good. Rotational velocity and blade position and rotation. Where's the blade at? Okay. Okay, everybody good there? Before I go to gyroscopic precession. Gyroscopic precession. Okay. CFI, do you explain gyroscopic precession to your candidates?
Yeah.
Okay, how do you explain it?
As a rotating body.
The propeller, like big gyroscope,
Okay.
and when we pitch up, or, pitch down, it puts force 90 degrees
To the force applied, yeah. Good. All right. Good. So in a rotating body, an applied force is felt 90 degrees later. Okay? 90 degrees later. A little bit like that caffeine high, it's felt about an hour after you drink it, right? So, that's a joke. Anyway, on a helicopter, the force is applied at 90 degrees. So if I want the blade to go up, force is applied here, but it doesn't affect it till here. Okay? What does that mean? That doesn't make any sense. Okay? So for gyroscopic precession, the force, why does it matter? Force is applied 90 degrees, 90 degrees later, or 90 degrees, the effect will be felt 90 degrees after the force is applied. Okay? So if it's applied here, it'll be felt here. If it's applied here, it'll be felt here. Okay? Why does it matter? Control inputs are 90 degrees out of phase. So if I want the helicopter to go forward, the adjustments or the inputs have to be put here in order to go here. Okay? I'll show you how this makes sense, hopefully, and then you can ask questions. Okay? What changes, or how is this change made? It's by the swash plate. Not squash plate, swash plate. Okay, swash plate. Hopefully I'll show you a picture today. Yeah, it'll be in a later lecture. How the swash plate actually moves up and down, and it has what we call PCLs, pitch control links, and that will, from the collective, okay, I want to go up, collective allows it to go up or down, pitch control links move it, but they are adding it 90 degrees right here for it to happen here. If you go look at the roadway, the pitch control link is on the right side, okay, right here, so that it will actually take effect by the time it gets to the 360 degrees, okay? All right, smarter every day, the earlier video.
Here's the question. If I have a helicopter and I simply want to make a maneuver and I want to tilt the helicopter up and forward just like this, how do we change the pitch in the rotor disc?
Where'd you go, dude? Come back.
So to me, it's logical that I would want to increase the lift on the back of the rotor disc. So what that would do is that would cause more lift here, which would cause it to tilt forward. This makes sense to me. Does it make sense to you? Well, here's the deal. You're absolutely wrong if it does. This is why. you actually provide more lift on the side of the helicopter, and that will tilt the helicopter forward. When I first figured this out, it blew my mind because it just did not make intuitive sense. But it has something to do with this little gadget right here. You may have seen one before. It's called a gyroscope. So what does this
What is your problem, dude? Play.
have to do with helicopters? If you think about it, it's a big mass spinning very fast. Look at a helicopter. What do we have on top? It's a big mass spinning very fast.
So when the rotors are aligned with the helicopter body, if I wanted to pitch the helicopter body forward like so, I would expect us to be in phase right here, and I would expect to take less of a bite with this rotor and more of a bite with this rotor to rock it over. Is that what
That's
happened?
not the case. It does seem like that would be, but due to gyroscopic precession, any force on a spinning disc, which
What? Anybody know why he's doing this today?
these blades do act as a disc, takes effect over a 90-degree phase. So if we give it a force here to push down or up to roll the helicopter forward, it'll actually take effect 90 degrees later and roll the helicopter sideways. So in order to roll it forward, we give the pitch on when it's 90 degrees away from.
Oh, so it's almost like predicting the future or something like that.
Something like that.
So if I wanted to rock the helicopter forward, I would take less of a bite when I'm 90 degrees out of phase and more of a bite over there, and that would do it?
Yep, so the blade here pulls up, this one pushes down, and it takes effect 90 degrees later when it's parallel with the machine, and the machine will rock forward
Alright.
like so.
Yeah, I'm not getting it either. In fact, I got a one-on-one explanation from an ex-pilot at the Smithsonian, and I still didn't get it.
The control tube 90 degrees in front on the swash plate.
Like everything on Smarter Every Day, I finally understood this when I made an experiment for myself.
All right, so Carl and I have set up a really super high-tech experiment involving bicycle wheels. Hey, the Wright brothers did it. It's good enough for me if it's good enough for them. And we have a camera aligned along a force application device, which is a metal strip. And do you want to explain what we got going on here?
Alright, we're going to...
Wait! I'm better. Go ahead.
We're going to apply a force straight up, and as you can see here, the tire rotates in the same plane as we're moving this bar. But when it's spinning, it's going to be different.
Let's just check it out. Yep. There we go. I used to play with my mom's exercise machine when I was like 5, so I'm highly qualified to apply angular momentum here.
There we go.
Angular momentum applied. It breaks.
Try to control
Alright.
this thing.
All right.
So now we're going to do the same test again. We're going to apply force straight up here, and it rotates 90 degrees from where we apply the force.
All right. This principle is called gyroscopic precession.
Correct.
And that's basically the force is applied orthogonal to the plane of rotation. It acts 90 degrees out of phase to that applied force. I think it's pretty interesting. So I have a plane of rotation here of the force, but it actually acts in this plane. And so if you look at the horizon that the camera's looking at as he...
Makes sense so far? So he's applying it here on the side, okay? So in our case, swash plate, and this one even has PCLs here. So you have a swash plate down here, so it applies it right here, comes up on the side, so your cables are on 90 degrees out, comes up here, woo, watch your head, comes up, and then where does it actually take effect? So if the swash plate is picked up by the collective pulled up, comes up on the left side, or sorry, on the right side, pilot's right, it's going to be felt right here, okay? So it's actually going to take effect. So he's lifting it on the side, but where's it actually taking effect in this case? The tire is coming up further 90 degrees out from where the force is applied. Everybody with that so far? Everybody get that? Or who did not get that? I'm not picking on you, just...
I get it, but does the angle change like every 180 degrees?
Exactly, yep.
So
As
when you,
as needed.
so when you go, once you do that once,
So that's why the pilot, so say they're lifting, okay, we're gonna transition to, we need to lift, force is applied here, but it's felt here.
right, but if that doesn't, if that stays the same, then you have force applied
Well, that and
in the next.
the
90
helicopter,
degree,
the helicopter needs forward momentum, so they're not gonna keep lifting, so then they're gonna transition to forward movement, so then they have air, fresh air, downwash coming through the blade once they've increased their forward movement. Okay?
Mike, are you asking if, so in there, he's pushing the force from the back. You're saying if you push the force 180 degrees, is that what you're saying?
You're saying right here, if the force was applied on this direction?
So how is the force being applied? Angle of attack of the blade?
Correct, yes.
So I get how if you put an action where he's at now, you
Yep.
have it at towards the house direction and that way.
Okay.
But then once it's there, what's to keep it from going back the next 90 degrees? Like, does the pitch angle stop that quickly?
Yeah.
Correct, yes. And also the swash plate, so this is where Aleo was kind of the same question, is blade design comes into effect, how the whole main rotor disc itself is designed, whether it has, if it's like a rigid one like this, or if it's a seesaw effect, where one comes up, the other one cannot come up, okay? Which would be a semi-rigid. Then you get fully articulating, where only some of them will come up and the rest can stay down. And that one's super cool, super agile, but you can't do aerobatics in that one. Okay.
All right, this principle is called gyroscopic precession.
Correct.
And that's basically the force is applied orthogonal to the plane of rotation. It acts 90 degrees out of phase to that applied force. I think it's pretty interesting. So I have a plane of rotation here of the force, but it actually acts in this plane. And so if you look at the horizon that the camera's looking at, as he pushes up, it rotates opposite of that. It's pretty cool.
Yep.
Anyway, that's it. That's why helicopter blades operate 90 degrees out of phase. Got anything
That's
you want to
it.
add? Besides the
That's
fact that I was kneeling in a horse biscuit the entire time?
Good job.
Hey horse, what do you know about gyroscopic precession? That's what I thought.
Here's the question.
Okay. So, yes, sir?
So have you seen that Red Bull helicopter?
Yeah. Well, I'll show you some,
You know how that works?
yeah, it works on the same idea as this one, actually. Same exact, where, well, we gotta get into blade types, and hopefully it'll make somewhat sense. Okay? At what position would force be applied to make the rotor disc pitch forward? Two.
Down, 4 up.
Position 4, if it's applied at 4, which way? Still confused? Okay, so 2 and 4. Okay, counterclockwise, 2 and 4. Force would be applied at 2 and 4 to make the blade pitch forward, okay? Still confused? Don't worry, it'll make sense as we get into rigging it, okay? There's a picture of me. Yeah.
So is the way the swash plate work, where as each rotor gets to position 4, it does that pitch?
Yep. All right, yep, let's go out to the roadway. In order to make the change, a change has to be made at 2 and 4. I think we get that. Has to be made at 90 degrees to the plane of rotation. 2 and 4 for forward flight to take place here. So 2 and 4 would be where it took, isn't that what you said earlier, Trevor? Yeah, so 2 and 4 is actually where it takes place. Okay? Due to gyroscopic precession, a helicopter's control input will be how many? 90. Good. I think I've said that like about 20 times. Okay. Translational lift. Translational lift. Rotor efficiency improves with forward flight. Why is that? Air, good. Same thing with our beach jet. Beach jet does not float very well, correct? What type of wings does the beach jet have, Nate? What type of wing setup does the beach jet have? Huh? High fineness ratio. So sleek, very long. They're long, but they're tapered out. They need a lot of air across the wings to get lift. Okay. Here in this case, we need air across the rotor plane or rotor disc itself to get lift. No airflow. We're akin to a rock, right? So, as you have forward flight, the tail rotor itself becomes more aerodynamically efficient. Instead of sitting there trying to hover, then we get a translational tendency. Oh no, we get this torque if we're just trying to sit there. Okay? Once we start moving forward, the tail rotor becomes more aerodynamically efficient, and then we get something called effective translational lift, where rotor moves from disturbed air into clean, healthy air, right? Horizontal air through the rotor disc. Air flows horizontally through a main rotor. Air flows horizontally. It's not perfect horizontal, it's like this. Okay. Here ETL, what direction is the air moving through the rotor disc? Yeah, which direction, vertical or horizontal? Horizontal, good. Auto rotation, because that's cool, right? So when you're flying along, Joshua, when you're flying along and the engine quits in a fixed wing, which is our airplanes out here mostly. So our airplanes out here, when you're flying along and the engine quits, what happens? What's the pilot's job? Glide. And so we have something that's called what? Best glide ratio. Best glide. Okay? Best glide is what? The distance that I can make it. I told you about my dad's A36 Bonanza. They were cruising along at 9,000 feet. Engine quit. Boom! Right outside Atlanta. He looks at it, types in nearest airport, 9 miles away. Best glide at that point was 8.5. They made it. 9 miles, just landed just outside Atlanta, best glide, types it in as fast as he could, pulls it up, and now the pilot was not my dad, he was flying my dad's plane, because as I was telling you, my dad gives out one of his planes to his customers as they come in. Pilot had about 22,000 hours, so types it in real quick, boom, and glided it in. So, what do we do in helicopter? Okay, you read your toes. Depending on how the helicopter is designed, they have something called, all helicopters will have something called auto rotation. Okay? It means that in the event that the thing behind you, the noisy thing behind you stops making noise, you still have a way for the blades to turn. Now, what does that really mean? You're falling out of the sky, but it's controlled falling. Okay? And because you're falling, you're not gaining lift, but something's happening with the blades where they're just flopping through the air to maintain a controlled fall. Okay? I said that in my terms. Okay? That's probably not what the FAA would say. So the pilot drops, okay, a helicopter descends the upward movement of the air through the rotor disc, drives the rotor blade. So typically air moves which way through the rotor disc? Wrong. How's it move? Normally, horizontally through the rotor disc. But in auto rotation, now we're falling through the sky, what happens? Now we got air that's coming up through it, okay? And so the pilot drops the collective. Now, the job of the collective is typically what? To control our up and down, okay? So they're dropping the collective, which naturally, as we're falling, the blades are going to do what? Give us a slight coning tendency. The pilot controls the rotor RPM with collective and controls airspeed with pitch attitude. Okay? Before skidding on the ground, the pilot flares to beat off forward airspeed. So, coming down, oh no, falling out of the sky. Okay, so coming down, and then right before now, we don't have a stinger on ours, but most helicopters you'll see something at the back there that hangs down. It looks like something that the kids would want to hang on. It's called a stinger, and that's to protect the tail rotor from colliding with the ground. So, comes down, and right before, they're going to do what? They're going to pull the collective just to bleed off and settle. Okay, so now you're falling through the air, but you're controlled falling because you have auto rotation. The engine is disengaged, but the rotor itself is not locked up. Okay, on an airplane, when our engine stops spinning, what happens? We're directly bolted here. Guess what? This thing will normally quit spinning. Okay, you may get, if the engine's seized, it will totally quit spinning. If it's like you've run out of fuel, the engine may, what they call free will. Okay, then we have something that we call what? On a constant speed, we can do what? Feather the prop, which turns it at a higher, lower angle in relation to the wind direction. Yes. So it will turn straight on so the air can smoothly go over the pitch angle. But with a helicopter, they have actually designed it so that it will just sit there and still free spin, okay? Free spin, even though the engine is not connected, okay? And that does that through the gearbox. I'll show you that in just a minute as well. What happens is they come down, they'll take the collective, and they'll pick it up just a little bit, just to give us a little bit of lift so that you can turn around and then settle it. Yes?
So when you're auto-rotating, do you then have the airplane tendency?
Not so much. Yeah, not so much. Well, yeah, as long as the main, the tail rotor's moving because they're geared together, unless you've sheared it. Yeah, that's a bad day then. But you don't have the torque of the RPMs. Yep.
Do these ever end up where it's like the helicopter's been destroyed, or is it pretty much just like?
Well, let's see. I think you should watch some videos. Okay, it's all about inertia. Okay, you guys ready? I got a couple good ones for you.
I'll kick it around. There you go. Now just fly it, just like you're doing, man. Beautiful. You picked your spot. Now you're gonna fight to get there. Wait for it. There you go. Nice. See how you milked that sucker in? Yeah.
Did you get that? Let's do it again just for fun, okay?
I'll kick it around. There you go. Now just fly it, just like you're doing, man. Beautiful. You picked your spot. Now you're gonna fight to get there. Wait for it. There you go. Nice. See how you milked that sucker in? Yeah.
All right. I think we should watch another one. What do you guys think? So you notice, I want you to notice the movement, forward movement when he decides to, okay, we're going to go forward. Now that the whole ship is moved, rotated in the forward plane, here it comes. We're gaining speed.
first segment is the level. In the AS350 models, the level starts when the tail is getting close to the ground. The longer the flare is held, or the closer the tail is brought towards the surface, the less ground run that will occur. The altitude for the level from the pilot's seat viewpoint is approximately 20 feet and depends on the amount of flare that's induced. When leveling the AS350 models, the aircraft is slowly brought to a nose-high attitude for touchdown.
Why do they keep pausing?
The collective is slowly induced during the level while still allowing the helicopter to settle. A common detrimental muscle memory that is developed from conducting power recovery autos is the reluctance to utilize sufficient collective during touchdown. The first portion of the skids to touch the surface are the spring extensions. The collective is manipulated to allow for a smooth touchdown. As the AS350 settles flat on its landing gear, the cycle gets displaced slightly aft and right. By following these steps and a little practice, you'll be conducting auto rotations like a pro.
Numbers, ground fast, hot and heavy. Nice. All right, let's see a real life. All right, pay attention to this real quick, okay? Hopefully you can hear everything that's being said.
Nice and eye level here to this spot. We want to make sure that as we're coming in for landing here, we're favoring the right-hand side, just in case anything were to go wrong. We have a bailout to the right. If we run out of power, there's sort of like an engine failure or anything like that. Yeah. All right. So this is looking really nice. Just coming in for landing. And engine failure. Ooh. All right. Shoot, okay.
Ooh, that was crazy.
Whoa, so mayday, mayday, mayday. Uniform Echo Tango, Uniform Echo Tango, Uniform Echo Tango. Okay. Thor, we're gonna be okay. I've got control here. Slowing down for the auto rotation. We want 50 knots. And so I'm just gently bringing it down to 50 knots. We're controlling rotor RPM. And all right, I've got a spot in mind. Okay.
Overspeed it. Why is it doing this?
And we're coming in. All right, this is gonna work just perfectly right here. Yeah, we're gonna do it. We're gonna do it. We're gonna be okay. Woo!
Nicely done, man.
We did it, buddy. Oh my goodness.
We're on the ground. That was insane.
We're alive.
Wow.
That's crazy. Wow.
What an experience, man.
Yeah. To this spot. We want to make sure that as we're coming in for landing here, we're favoring the right-hand side, just in case anything were to go wrong. We have a bailout to the right. If we run out of power, there's sort of like an engine failure or anything like that. Yeah. All right, so this is looking really nice. Just coming in for landing. And engine failure.
Ooh.
All right. Shoot, okay.
Ooh, that was crazy.
Whoa, so mayday, mayday, mayday. Uniform Echo Tango, Uniform Echo Tango, Uniform Echo Tango. Okay. Thor, we're gonna be okay. I've got control here. Slowing down for the auto rotation. We want 50 knots. And so I'm just gently bringing it down to 50 knots. We're controlling rotor RPM. And all right, I've got a spot in mind. Okay. And we're coming in. All right, this is gonna work just perfectly right here. Yeah, we're gonna do it. We're gonna do it. We're gonna be okay. Woo! Christy Thun, man. We did it, buddy. Oh my
We're
goodness.
on the ground. That
We're
was
alive.
insane.
We're alive.
Pretty amazing.
That's crazy. Wow.
What an experience, man.
Yeah.
All right. So, pretty cool. Yep.
Does the auto ignition spin the same direction as a normal flight?
Why is that?
Because if it stopped and switched directions, it wouldn't be
Lift. Yeah, we got to have air over that airfoil, not foil, airfoil, right? We got to get air over the airfoil. Yes.
That was actually a training exercise.
Was it?
Yeah.
That's just sick, dude.
The video, if you can watch it, it's overacting.
Huh?
They're acting.
Really? Dude, that's sick. Anyway, that was pretty amazing. Crazy. All right. Here we go. Little sheet metal project for Josh here. All those who enjoy sheet metal. Finney, your favorite subject so far, right? Here we go. We want a little sheet metal project. Could have flared a little more, you know. Flared a little more, a little less, but guess what? But you know what? They're walking away from it today, right? Any questions so far? Everybody?
I'd take a shoot on one of those over a Sears.
Probably so, yeah. All right, so our four forces are what? Lift, thrust, weight, drag, or lift, weight, thrust, drag, whatever. Induced flow and transverse flow. We have ground effect. What are some acronyms that we use for ground effect? Iggy and Ogie and Higgy and Hoagies. Okay, good. Everybody hungry now? All right, we have translating tendency. What is a translating tendency? It's not English to another language. What is it?
The tendency for the helicopters to move in the direction of the
Opposite direction of the tail. Okay, good. And then coning. Yeah. Think of ice cream cones. Cones, big, wide cones. Okay. All right. Coriolis effect.
As it cones, it spins faster.
Spins faster. Oh no. Think of the figure skating. Woo! To get the same torque, we got to go faster. And the danger of that is our massive loss or rapid loss of rotor blades in the event that we overspeed it, right? Bolts and nuts and cotter pins that you put in come off if we overspeed it, okay? Gyroscopic precession. Does anybody understand it? Okay. All right, and then we have translational lift versus effective translational lift. What is the difference? Which one's more effective? Effective because clean air is coming through the, come on, why am I giving you the answers? Clean air is now is actually going through the rotor disc itself, okay, horizontally through the rotor disc. And what is auto rotation? It's your last chance at life, right? Yeah, last chance at life. Okay, take a break. Why don't you come back at, let's give you till 10 after. Let's do it. Corbin coming back?
Pearson.
Okay, I did not need. All right, so rotorcraft types. Now that we've talked about the spinning things and what the physics of it is, which is still a little bit blurry for some, me included. Power plants, that's the cool stuff. That's what we need to know about, because we have to work on those. The drivetrain itself, main rotor types, tail rotor types, and intermeshing. Intermeshing and coaxials. Okay, we won't get through all of it, but we'll get to going, okay? We're at slide 44 of 102. Students can identify basic helicopter components. That is a blade. Good, hope you could tell that. All right, any questions thus far? All right, here we go. So we're rotorcraft types, boom. What do we name that type? Good job, it's a rotorcraft. What type is it? This was Cessna's grand design that they would said, hey, we will sell this to the military. Isn't it a 172 with the stinking mask going through it? Yeah, it's like, hey, let's put a pop top on it, and better yet, let's just stick the mask right between the pilot and co-pilot. Do you see that through the glass there? What is this thing going right between them? Oh, you know what? That little thing beside us, let's just put the mask right through the cockpit. And so this is called the Cessna Skyhook, and no, it did not sell the military. They were smarter than that. Okay? So.
How would weight and balance work on that? The engine's still in the front, right? If the engine's still in the front, where's your weight in the rear?
I don't know where the engine's actually. Well, your fuel could be your weight in the back. But, you know, it didn't sell, so don't worry, okay? All right. The Skyhook. Cessna Skyhook. Whoa. All right, so let's talk about landing gear first. Landing gear, the cool thing about a rotorcraft, you're not going anywhere, but you can land anywhere. Right? Get the joke there? Because they're not really going through the air very quickly. You know, you buy helicopters. What's the point of helicopters? To spend money. So here we have helicopters that you actually do have a actual landing gear. And then over here we have skids. And then on this other one we have like actual bumpers that are changeable. So that's super cool unless you do auto rotation. And then they'll be a little harder to get off with it. Tail skid. Also, the protectant for the tail skid is called the Stinger. And it's just a cool name there. Okay? Everybody good there? All right. We have autogyros or gyrocopters, which a lot of people will say that's not really a helicopter. Okay? So if you talk to a rotorcraft pilot, that's what they'll call themselves, rotorcraft, and they're rotor wing and we're fixed wing. Okay, whatever. They'll say, don't insult them and say, oh, that's cool, I fly a helicopter too, it's called a gyrocopter. They'll probably laugh at you. Okay? So it's a free spinning, but the reason why a gyrocopter is they're going to need their thrust from the aft engine, right? So anyway, we have this gyrocopter. We have a single rotor, main rotor with a tail rotor for anti-torque. And then we have tandem rotor, fully equipped with air conditioning. Yeah. Okay, so it increased useful load, counter-rotating, so one goes clockwise, one goes counterclockwise to set the torque off. Okay? This one was factory installed air conditioning.
So the main rotor is not powered?
What?
But it says free spinning, so.
Oh, yeah. Yeah, for the gyrocopter, yes.
Yeah.
So that's why I said is that most of them will say, this is not really a helicopter.
So where's our lift coming from if that's
So-
I missing something?
Well, gyrocopters are interesting because you'll see people with, you'll get this whole thing where you get powered parachutes, where you're running an engine, and then they're running spooling gyrocopters where it will actually, some of them are geared to a certain gear ratio where the engine's spinning, and then they'll be spinning, and then some are actually just rotating as the air is going through. They'll move it, and as they increase RPM of the aft engine, then your airflow is going to be like this type, like an auto rotation type, where it's actually cutting through and you're just changing the pitch to gain more lift as you're going through the air. So the reason why a lot of times on the gyrocopter they don't include it is because you don't have that horizontal component. It's more of a auto rotation all the time with the main aft thrust engine pushing. Okay. Yep.
How does the 90-degree work with their two degrees?
You know, I think it'll make more sense when we get into the gearbox, how it actually works in the gearbox. So, give me a little bit of time to get to that. I don't even think I'll get to it today. It'll probably be tomorrow for that question. Yeah. So let's just hold on for right now. I think if I started on it, it would only make frustration, okay? All right, so turbine versus recip, right? Why turbine? Better power to weight ratio, right? Because we want lighter aircraft. They're not going faster, though they could. Better performance, less vibration, okay? And then higher reliability. Here's Sikorsky with his recip, he's the first designer of it. And then this is also his first power turbine helicopter over there on the right. Somebody speak French in here? Alouette? Alouette? Right? How would you say it, Nate? Cameroon, were you the French side or the English side of Cameroon?
French side.
Oh! Alouette? How do you say it? Alouette, okay. So, anyway, this is Sikorsky's Alouette on the right. Power plants, reciprocating. This is where I don't feel like I gave you everything because I'm not trying to overload you. But I could get into really gory details here. So you have the Robinson power plant reciprocating O360. What does the O stand for? Opposed, meaning the cylinders oppose each other. They're across from each other. What is an inline engine, Joshua? Good. Straight down the middle versus opposed, Gavin. Cylinders are opposite, just like this style here, where your cylinder would be here, and then on the opposite side of the case, or what we call the block, in automotive world, the case would be another cylinder. So they use an O. Now, Lycoming loves abbreviations. They actually have over 642 if you're counting. So they'll have O, they have IO, injected opposed, they have VIO, vertical injected opposed, and so you may see with helicopters, you may see vertically injected opposed or vertical opposed. Then you have LVIO or LVIO, left-handed vertical injected opposed, or LIO, left-handed. So depending on how it's rotating, okay? 0540 is the big brother. It's the Lycoming R44 series, 6-cylinder, going on the 44. Is that what you guys had? 44s? You had 44? Yeah. So 540, turbo or non-turbo? Non-turbo. Wow. Okay, and then you have the Rotaway has their own concoction. It was liquid cooled opposed liquid cooled. And then you had the IO390 from the Instrom, the IO360 from the Schweitzer 300, okay? Everybody good so far? All right, here we go. Now we get into the big ones. We have Lycoming. They had their own for the turbine engine. They had a Bell one that goes to the UH-1H, the Allison. We have a PT-6, 37 A's. You have, Eurocopter has one, Allison has one, but they're single engine. We have one on the shelf. PT-6, it looks just like this with a helicopter gearbox on it. It's just, it's actually the first shelf up, all the way on the left, and have a gearbox just like this. Okay? Power plant, twin turbine. So we have two engines, because bigger is better, right? And so they'll do two, it could be two Allisons, they could be two PT-6s, two Lycomings, two GEs. Super cool, right? Because bigger is always better. All right, so they're running two engines now. Now we get to three engines. Yay! Three engines. So we get to the Boeing, we get to the Av chopper. So when this one goes down, guess what? Oh man, I need $6 million now for engine overhauls. So, no, the overhauls hopefully be a little cheaper, but not much. What's the cost of operation? Hey, we're going 150 miles an hour, and the cost of operation is only $5,000 an hour now. Because the average cost of a beach jet is what, $2,300 an hour, and you can go 480 miles an hour. And so, hey, we're finally getting 150, and it's only costing us $5,000. Bang for your buck there. But you can land anywhere, which is super cool. Okay? All right. And we don't stop there. What do we do? After three, we go to? Because we must get bigger. And this is the Russian types. And so they said, you know what? Why not go all out? Let's just do another engine to it. So the Russians added a fourth engine to it. Here's the Homer. You don't need to know it. I just thought you'd like to see a four engine. Okay? Four turbine rotorcraft. It looks like it should never fly. Correct. Caproni's invention here. No, not at all. Okay, so name a single engine recip helicopter. R-44. R-22, good. Okay, name a twin engine helicopter. Okay, you got Chinook, you got a B-212, you got an AW-109. Good. Okay, do you need to know those? All right. Helicopter drivetrain, how does it do what it does? And it does do, oh no, what was, how does the song go? Come on. It does do what it does do, and it does do it well, or it does, how did he sing, Buddy Davis? Come on, some of you guys had to listen to that. Okay. So, do you control the speed of the tail rotor? You betcha. How do you control the speed of the tail rotor? By the main rotor. Good. Gotcha. All right, so it goes to the gearbox, and it's geared, or geared, to the tail rotor speed, or to the main rotor speed. The tail rotor's geared to the main rotor speed, okay, through a gearbox. And so we get this belt system, okay? Did I cover all my notes there? Yeah, okay. So we get to a belt system. Belt systems couples engine outputs to the drive shaft. Tensioner engages. So what happens, sometimes you'll see a helicopter and it'll spool up, especially the turbines. Okay? And then you're not really seeing the blade do anything. Why is that? Because the torque converter has not been engaged, okay? So they'll have sometimes, like our rotorway out there has a belt drive system. So they'll actually run a belt to drive the main rotor, okay? Sometimes they'll have to even engage, or what they call a tensioner, to engage it once it's reached a certain level, okay? Because a turbine really is not efficient at low RPM jet. You got to get it spinning. You know, we got to turn that bad boy because faster is better, right? It's your mentality on the way to school. 7,000, 8,000, finally we can engage the rotor, okay? On the smaller ones, they'll engage it. They may have a a hideous tensioner like this, and then they'll slap that bad boy, and all of a sudden we've engaged the main rotor, okay? Clutch actuator. I did, in defense, we did watch one student who thought, hey man, I can't get the belt out of the rotaway, so what's the best way to get the belt out? Cut it. And we just sat there and said, so how are you going to get the new one in? What length was it? All right, great. Lesson learned. All right, so actually Rotaway even ran a belt from this drive mechanism all the way to the tail. Anybody see a problem with that?
Stretch, flex.
Oh yeah, there's a little bit of play. Oh, you know, because 10 feet we won't have any give, right? Can you imagine trying to tension a belt 10 feet long? You can't even tension a sticking alternator belt. Tension a belt that's 10 feet long. So. All right, drive belts. They're honking huge. Some of them are massive, like that big. Okay. Now, combining. Do we want to run a belt system with two PT6s? Probably not. Okay? And because the turbines turn so stinking fast, we've got to reduce it. So we combine or we marry, some of you might be getting married soon, Brian, marries engine output into one gearbox, right? So they'll go into two-sided gearbox. They'll marry inside the gearbox to produce horsepower, to combine horsepower there. So here's our main gearbox. We're running two outputs from the engine. Okay, what's the problem with that?
One quit.
Say what?
One quit.
If one quits, hopefully we get enough mojo to maintain altitude. What else? More moving parts, more expensive. We also have to be able to disengage two in the event there's a problem. We got to auto rotate, okay? But we do have a backup. But we have to be able to disengage if there's ever a problem, both of them, for auto rotations required. So, pretty crazy. All right, notice here is our Chinook. We get two bad boys on the outside going to a giant gearbox. We got a rotor here. Boom. How does it work? I don't know. Super cool. All right, this is where the Southern English is going to come out. Hopefully you'll enjoy it. Sprag clutch. Freewheeling sprag clutch allows the engine to be started without a load. As I said, I already alluded to it. Pretty needful because we don't want to start a PT6 and have a load on it at, what, 200 RPM. Not very good, okay? So it allows the engine to decouple during power loss, but it also allows us to start. So we have a sprag clutch. So it's these little teeth, and so it will spin and it will be disengaged, and all of a sudden when it turns, when the engine's actually turning, it will turn the gear the opposite way as it engages, and these little bitty teeth will come out. I'll show you a video of one so you can see how it actually operates. Okay, these teeth will engage like a clutch and cause it to spin. So here, aren't you mesmerized by the what do they call it? GIFs or whatever. Similar to a bicycle. So you're on your bicycle, you get in your 10-speed. Okay, you're riding your bicycle super fast, and then all of a sudden, what do? You let off. Come on, you guys look at me like I'm an idiot. Come on, what do you normally do though as you're riding your bicycle? Oh yeah, I'm so fast, and all of a sudden you let off. You go backwards. Why does it do anything backwards? Why does it do anything backwards? Because of a sprag clutch. Okay? Because of a sprag clutch. Because a sprag clutch does what? It says, oh, no, we're going to disengage. And all of a sudden you go, oh, go faster again. So you're going to go faster again, and it engages. Oh, I'm going to engage the clutch again. And then we go, backwards. Then you've disengaged the clutch. Okay? All right, was that animated enough for you? This is better than that. Good animation, okay? All right, freewheeling sprag clutch, okay? I know what you're thinking, Tim Peak. What am I looking at? What am I looking at? Okay, well, I'm glad you asked. So this is a Sprag clutch system. Let me show you how it works here. All right, this is a pretty stinking awesome video. I want you to kind of stay with it. Okay, this is 2-engine gearbox to the mast. Okay, so here's an engine output, another engine output. Okay, going in here. So it's going to have 2 different Sprag clutches. Super cool. Okay, so pay attention here.
Okay, so today we're going to talk about the freewheeling units that are found on this transmission and every helicopter that's designed. The freewheeling unit is necessity. So if the engine were to quit, we want to make sure that the main rotor continues to turn for auto rotation purposes. But we don't want the drag or the failure of the engine to cause the RPM to drop significantly. We need a way for the engine to drive the transmission, and so that the transmission cannot drive the engine. All right, we need a disconnect. So this is the freewheeling unit here, and there's 2 of them on this transmission because this transmission is designed for a twin engine aircraft. This here is the output for the tail rotor, and this is where the mast would normally be located. Okay, so this transmission's from a Bell 205, 204, 212. We're going to have the input from the engine here, and the output will be through the mast and out through to the tail rotor here. So think of the freewheeling unit like your bicycle. So with your bicycle, you can pedal and you're going to turn the rear wheel, but as soon as you hit that hill and you start to build some speed, you don't want your rear wheel to spin your pedals. You want to be able to stop pedaling, all right, and just concentrate on going down the hill. Same thing happens here. We want the engine to drive the transmission, but we don't want the transmission to try to drive a dead engine. So this is a close-up of the freewheeling unit, and as I rotate it here, you can see that as I turn it, so this is to simulate that the engine is driving the transmission. You can see that the tail rotor is turning here, so the output to the tail rotor is turning, and the output to the main rotor would be turning as well. But if the engine were to quit, we would want the main rotor to be able to continue to turn. So if I was just to keep turning this, if the engine were to quit, notice that the tail rotor could continue to turn and the main rotor could continue to turn, but the freewheeling unit would disconnect the engine. So this flange isn't going to move because the freewheeling unit is located right here. So driving, and then if I rotate in the opposite direction, of course, there is a disconnect there. Same thing happens with this side over here. Driving, you notice the other engine is not going to be driving because we don't want this engine to have an output to the other engine. We want both engine outputs to the transmission. So we're simulating right now that the engine on the right-hand side, the number 2 engine, has failed. The number 1 engine is still working, still driving the tail rotor, still driving the mast, or not driving the input on the other engine. Okay. Engine input here, tail rotor down below, main rotor mast. Engine is driving the main rotor mast and tail rotor output, but if the engine were to quit, the freewheeling unit is located right here. We'll disconnect the input flange from the transmission itself so that you can see there when I turn the tail rotor, the mast is spinning, everything's spinning inside the transmission except the output to the engine will be disconnected. So this freewheeling unit is from a Bell 206. Bell 206s work a little bit differently where the freewheeling unit is located inside the engine. Even Even though this freewheeling unit is installed in the engine on the Jet Ranger and normally in the transmission on most other aircraft, it still needs to be supplied with transmission oil, because if the engine quits, we want to maintain lubrication in the freewheeling unit. So lubrication will still be coming from the transmission. Engine output on these splines, which are going to drive this shaft. This shaft will drive the output shaft. So they call this the outer shaft and the output shaft. So I'm going to apply a force right here on these splines, and you can see that the output shaft wants to rotate. What happens if I want to keep rotating? In this case, I want the main rotor to continue to rotate, but I need to disconnect from the engine. Notice that the output is allowed to continue to turn, but the input will be stationary. So that would be simulating an engine failure or an engine seizing. We want the main rotor to continue to spin. So let's take this apart. So you just slide it off ever so gently. Expose the shaft. I'll lay that down. So there's the output shaft. There's the outer shaft here. And inside we have sprags. You can see all those sprags here. In one direction they're going to stand up. In the other direction they're going to lay down. They're all spring loaded. And they take up that gap that's in between the outer shaft and the output shaft. So that space there, it's very important that these sprags be of a certain dimension. So even an aircraft that auto-rotates often, like a training aircraft, these will wear out quicker than a typical normal utility aircraft. And that's because they're performing so many auto-rotations. So when they're slipping, they'll begin to wear down the sprags. There's the sprag unit there.
Looks like a needle bearing, doesn't it? With teeth.
Sprag unit consists of many sprags. They have to be in the correct orientation for them to operate. And you can easily tell if when you're assembling one of these after maintenance that you have one in the wrong direction. So you can see that they want to lay down or stand up. Laying down is going to create a smaller overall diameter, and it will allow for slippage of the two shafts. But when they're standing up, it looks like they wedge themselves into place. They take up the gap, and then you create one shaft that can drive the other. We can just drop those in here ever so gently, get them in the right position, and they should fall right in. There it goes. And they drop into place. Shaft goes inside. And there we go. Driving, freewheeling.
All of your power is going through 30 little door wedges.
On that bell, yes.
That is crazy.
It is so crazy.
Do those sprawl clutches have a service life?
I'm sure it's just like aviation, like all of aviation, depending on who made it and what they say. Yeah.
More of a reason not to fly a helicopter.
Somebody pat him on the back. Comfort him. Okay. What's the main purpose of a freewheeling unit? Freewheeling unit.
Allow for auto rotation.
Allow for auto rotation. What's does it does?
Start up without a load.
Yeah. Good. So allow rotor to turn independent of the power plant. Auto rotations, or as I said, can you imagine if you had to start a turbine every single time with a load on it? And it's wearing on those bearings just.
But at that point, you're not going in an opposite direction. Does that mean those teeth don't engage at a certain speed?
Yeah, so it's oftentimes, this may be terrible to explain it this way, but this is the way my mind works. But on like a car, you have a throwout bearing where you push in the clutch, and it will push the bearing into it. And that's kind of the idea here when you're wanting to engage, where it pushes down okay, I'm ready to engage the sprag clutch to drive it. Now it will engage it, and sometimes it will even push it down onto the shaft. So while it's spinning out there, it won't be engaged, and then to use like, do you know what I say? What I mean when we don't drive we don't drive manual transmissions anymore, do we? But, throw out bearing will actually, you push the clutch and it engages it. Clutch, you're going to engage it in this case to engage the main rotor then. Okay, I pulled it in. Not on the bell, but some of them, yeah, to engage it. Yep, correct.
Is that like some like rotor brakes? Yeah.
No, I know what you're talking about. I don't think so. No. That one was, yes. And as I said, even when I was trying to look at, there's just so many variables, whoever made them. Yep. Main transmission and gearbox, MGB, main gearbox, main gearbox. Transmission transmits engine power to the main rotor and to the tail rotor. Okay? So main rotor and tail rotor gear ratio is different. Which one spins faster? Tail rotor, good. Independent oil supply, they'll have independent oil supply. So even on the tail rotor gearbox, you'll have its own oil supply. Okay? And hopefully a sight window. And hopefully you'll check it more than you do your drivetrain oil in your car, right? Because nobody does that, right? All right, accessory drives, we have main rotor tack, hydraulic pump, and rotor brakes. And then we'll have chip detectors. Every gearbox will have a chip detector. What is a chip detector? It does detect metal. Okay, as metal particles come apart inside the gearbox, you get a certain amount of metal that's flying around in the gearbox, or floating around rather. All of a sudden it goes to this chip detector, which is reading resistance, and says, oh, whoa, wait a second. I've got so much metal, I'm going to set off the light and say, uh-oh, we have, and it's not one of those things that you just pull out and clean and say, hopefully it won't come back on. Okay? When the light goes off, you got to say, oh no, there's a problem. Parts are falling apart inside the gearbox. And so we need to figure out why. It's nice for us. Look at this dude standing beside this main gearbox. Mega. Okay. So we have mast, drive shafts, and drive belts. Mast is typically hollow. Like I said that? Typically hollow. Typically hollow and transmits power to the main rotor. Drive shafts transmit power to the tail rotor through flex couplings. Okay? Why is the mast hollow? We want, well, the mast, the main mast. Why is it hollow? Is because weight reduction. Imagine if you had, oh, I've got a 3.5-inch piece of steel spinning through the middle here. That's a great idea. No, and then we have drive shafts, transmit power through flex couplings. Here's a flex coupling, okay? Why not run just a solid shaft all the way to the tail rotor? Why not just run a solid shaft all the way to the tail rotor? Heavy. So what? It flexes. It flexes like a Boeing wing. Right? Yes, what was your question? I guess gyrocopters, they tell you to wear a parachute just in case. So. Yeah. Sorry, that was a little funny. Okay, drive shafts have to have balance weights, okay? So flex couplings, the reason why we have flex couplings, and you'll see them even on our bell out there, lots of flex couplings going all the way back, is because there's a lot of movement. And there's a telltale sign. What do you see with this one right here? What do you got here? You got all it's throwing its guts up, okay? So it's got grease coming out. So we know probably that that bearing is done, okay? And so for us, it's a telltale sign that, okay, the bearing itself, flex coupling is going out. We got to change that, okay? And so they transfer loads to the back. And then belt drives, they must be tensioned, okay? Belt drive must be tensioned as time goes on. Okay, gearboxes. So gearboxes, what's the purpose of a gearbox? Is to change direction. Is that simple enough? Okay, so we have a 90 gearbox. We have 90 gearbox on our rotorcraft. We have 90 gearbox on our bell. And what does it do? Simply goes out to the back of the tail of the airplane here. Oh, here's one right here in front of you. And as the tail rotor has this shaft that comes out here, what does it do? It turns at a 90 degree. The gearbox changes the direction. So we have a 90 degree. And there you're going to have chip detectors, and you're going to have an independent oil supply. Okay? So on the bell itself, you should be able to see a little window. It shows you the oil level for the gearbox up here. Now, if you need to, you may have an intermediate gearbox, because now you want to put the tail rotor further up on the vertical, okay? So we want to put it higher up on the vertical, so you put it way up here. So now we need an intermediate, sometimes referred to as a 4240 gearbox, okay? So intermediate, just changing directions again. So what does the transmission, what system does the transmission send power to? Parker?
Tail rotor.
Sends power to the tail rotor, main rotor. Good. Two types of gearboxes. Herson, give me a type of gearbox. Degrees one. Okay, John, give me another.
4244.
Good. Intermediate or 4244. Good. I don't know if I'm going to start another section for you. It's a long. All right. I will just barely start the second section here. All right. Okay, blade construction. We have the tip, we have the root, and we have the twist. Okay, so here is the one off a Robinson that had a collision with a golf cart. Okay, so this is the tail rotor. And so just like our wings, we have a cord line across them, and there's slightly different angle depending on especially you can see that on the bell, where you have a slightly more asymmetrical airfoil over the top of the bell rotor. Okay? Blade construction, man, you can have wood. I don't know if that's a good design anymore, but you could have wood. Okay? You could have spar rib fabric match set, but problem with wood, can get water in it. Okay? Metal blades could replace individual blades. They're life limited because metal, what happens with metal? Fatigue, yeah, corrosion, good. Metal skin bonded to honeycomb. In here we have a honeycomb. We have a honeycomb construction. Please pass it around, but don't hurt yourself, okay? So we have honeycomb construction. This one's just on the leading edge. Some of them have them on the trailing edge as well. And then at the front of it, you may have a metal leading edge. Something like that. Could be composite leading edge, or it could be metal leading edge. Okay. What's the fastest helicopter ever there at the bottom? Come on. No, Osprey's a slug. Oh no, it's there. What is that? When it falls, great. No, this is a lynx. A lynx. It's set the record, it held the record for the last like 30 years. So if you plan to go fast in a helicopter, think again, unless you're falling straight, as Brian said. So 249 miles an hour. Now they have designed helicopters, actually a hybrid, that was faster. They came out last year, and then they tried to sell it to the government. Government said, yes, we want it. Then the government said, what? Nah, we don't want it now. So they did have it. It had a main rotor at the top, and it had 2 more jets on the back for pushers. And so it was a turbine. So what would happen was you use a helicopter to get up, and then you turn the bad boys on, and you're gone. And it ran about 328. But because it was a prototype, it wasn't a real helicopter, right? So the technology's out there. It's just another part of those conspiracies. Okay? All right. So the Lynx, though, did a burp tip blade, which was super cool. Do I understand it? No. All I know is it made some kind of weird honky-donk at the end here. Okay? And so it came around, and the way that it sliced the air allowed it to go super fast. So it set the record. Leading edge can be made from harder materials, wear strips or abrasion strips, and can be foldable. Okay? Foldable. They can actually fold those blades back. But they got to be pretty robust. And you're talking like the sky crane, and there's just screaming as it carries a load or picks up a load. Yeah. So, super cool. Any questions, comments? All right, you guys, I'm going to kick off right here before we get to main rotors. So tomorrow we'll come back to main rotors, where we have rigid, semi-rigid, fully articulated. Okay, get to those tomorrow.